Today I'm going to show you how to formulate and solve a simple linear programming problem in MXX Excel. Because linear programming is a very useful technique, and very often people are not able to use it because the formulation is a challenge. In this presentation, I'll give you a brief overview of how one can formulate a linear programming problem in Excel and go through the process and make you understand how it works. Now, to give you a brief about linear programming. So linear programming is an optimization technique wherein an objective, which could be either a maximize or a minimize, is optimized given a set of certain constraints. So linear programming is essentially an optimization technique. So for instance, if you want to maximize profit of a firm or an enterprise, you could use linear programming. Alternatively, it could be minimization of cost. You could use linear programming. In fact, linear programming is used in feed mix problems to minimize the cost subject to certain minimum standards of nutrition being met. The typical formulation of a linear programming, it consists of three parts. One is the objective. Now, the objective could be either a maximization or a minimization. It cannot be both. So it's either a maximization or a minimization. And it's formulated like this, where it is C prime X, where C is a vector of coefficients. It could be profit, it could be cost, it could be just about anything. X is a vector of decision variables. So if you've got many activities, so each decision variable will have an activity, which you will see in the example. Now, this objective is satisfied based on certain constraints. And the constraints are A, which is a of input-output coefficients, and B is a constraint. And there is one universal constraint which says that X should always be greater than 0. So X will not take, the decision variable will not take negative values. Now, we solve linear programming problems in a very useful utility, which is found in MS Excel. And that utility is called Excel Solver. So it's a utility in MS Excel, which is very useful for solving linear programming problems after they have been formulated. It usually has to be installed before use. So before you use Excel, you have to install it. And I'll just show you how that is done. So first you go to Home. Open an Excel sheet, go to Home. And in this Home, that is, it's a second button, the first button, which is Home. And in this Home, at the bottom, you'll get something known as Options. So when you click on these options, this window opens on the right-hand side. So in this window, you have to scroll down and choose this add-ins. When you click this add-ins, this window will open. Right? This window will open. And when this window opens, at the bottom, you have what is called as Excel add-ins. You say go. You say go, and then you get this screen. So it says Analysis Toolpack if you wanted to select it. Analysis Toolpack VBA if you wanted to select it. If you want euro currency, select. But the main important thing is you should select the solver add-in. So to make Excel solver work, this has to be ticked. And then you say OK, and you're ready to go. So that is how solver works. This is how solver is to be installed. And once solver is installed, this is your screen. We started with file. We started with file, and that's where we added. Now, once solver is is installed, you should go to this data icon. Click on this data on the menu. Click on data, and then solver will open. And then solver is there, right? And once you click solver, you're ready to go. This screen opens, and this is where you formulate a linear programming problem and solve it in Excel. Okay, so that's as far as solver is concerned. We'll now talk about linear programming. Go back to linear programming. Now, linear programming, before we fit linear programming, we should know that there are certain assumptions. Sometimes the assumptions can be limiting assumptions, which will be limiting in the sense your result will not be realistic. So the assumptions are linearity, the basic assumption that input-output increases linearly. It is not a curve. It is 1 unit of input if it brings 3 units of output, 2 units of input will bring 6 units of output, 3 units of input will bring 9 units of input. So that's what you mean by linearity. The input-output relationship is linear. Second is divisibility. Now you have linear programming, you have decision variables. Decision variable can be products. It can be anything. It depends on what you want a result of. Now that can take fractions. That's what it means. It need not be round numbers. Like for instance, if you're talking of a number of people to be employed, you can get a optimum figure like 1.3 people, which may sound unreasonable, but that is the problem. There are ways of overcoming that. That is what is called as divisibility. Then there is a third assumption is the assumption of finiteness. And what finiteness says is that the number of alternatives that you consider while solving a linear programming problem is given. That is all there is to it. There's nothing more. So it will not look for a variable outside the what you have suggested and then find a solution. And a unit value or a single value expectation means that whatever coefficients you assign to the problem will not change. They will be same. And if they have changed, then you have to run the program again. These are the assumptions of linear programming. So linearity, of course, is a very, very stringent assumption, which of course there are ways of overcoming linearity by variants of linear programming, which we discuss later. Divisibility can be handled with integer programming, where results can be obtained in round numbers. And finiteness, of course, you have to consider everything. So that is within the hands of the researcher. And and finally, single value expectation means this that the values don't change. Open an Excel sheet, and this is the Excel sheet that I have. So I'm going to demonstrate how linear programming is to be formulated using an agricultural example where on a farm you can grow crops like paddy, maize, irrigated maize. So now supposing you have an irrigated maize, then that has to become as a different activity. So cotton, then there's irrigated cotton, jowar, groundnut, soybean, red gram, red gram, and dairy. So these are my decision variables. These are my decision variables. Okay, these are my decision variables. Now, now I want to. This is a maximization problem where I want to maximize the profit from this agriculture activity. Right? So I uh, I know the profit that I can get from 1 acre of paddy is 12,600 and 12,560. 1 unit of maize, one acre of maize, I can get 5,680. And from maize irrigated, I can get 7,000, so on and so forth. These are the profit figures which I'm going to use in my objective function. So these eventually become the cost coefficients, which I showed you in that presentation. In the presentation I showed you, these are the C coefficients. X is the decision variable. You've just seen that. These are the X's. And these are the constraints. Now I've got labor. I've got 105 units of labor. I've got 64, I need 64 units or man days. These are called man days. So I need 64 man days of labor to produce a unit of maize, of 1 acre of maize. And I need 70 man days to produce 1 irrigated acre of maize. And the cotton requires 120 man days. Irrigated cotton requires a little more, so on and so forth. So this is my labor requirement. This is one constraint. Similarly, have another constraint, working capital. Because other than labor, I'm using fertilizer, I'm using pesticides, I'm using plant protection chemicals, I'm using a whole lot of other things which I capture under working capital. So to produce to produce 1 unit of paddy, for to cultivate 1 acre of paddy, I need 43,560 rupees. To cultivate 1 acre of maize, I need 9,875 rupees. So on and so forth. These are the figures that I have for various crops. Then agriculture produces byproduct. Now, from 1 acre of paddy, I get 12 quintals of byproduct. Then from 1 acre of maize, I get 20 quintals. 1 quintal of irrigated maize, I get 25 quintals. Then 1 acre of jowar, I get 20 quintals. 1 acre of groundnut, I get 2.5 quintals. And I require, for every dairy, I require 12 quintals. So I'm just keeping that here. So one animal requires 12 quintals of fodder in a season. Now, this is all for a season. Now, dairy, if you're going to have dairy, dairy is also going to produce byproducts. So one paddy requires 20 quintals of farmyard manure, which is produced by livestock. Maize requires 15. Irrigated maize also requires 15. For the others, I have not put. And the animal produces about 30 quintals or 300 quintals. And one animal produces around 300 quintals of farmyard manure in that. These figures can be changed. These are not exact figures. They're just to illustrate how a linear programming is to be formulated. So in a farming situation, a farmer may require at least he wants 1 quintal of paddy for his house requirement. So when I grow paddy, I want to eat only the paddy that I've grown in my farm. So I need 1 quintal of paddy. Similarly, I also need dairy. For a whole season, I need about 120 liters of milk. So roughly 1 liter of milk for 120 days, which is the season. I require uh, this. Then I should know what paddy, how much yield it is going to produce. It will probably produce 35 quintals per acre. I don't require it for the others because my requirement is only for this. And similarly, for the requirement of dairy, I know one dairy animal will produce 720 liters of milk per season. Okay, so this is how the linear programming problem is the data. This is the data that I need to generate in order to formulate a linear programming problem. Now, what I will now do is I will take all these enterprises to another Excel sheet. Okay, I'll take it to another Excel sheet. I'll place it here. I will be special and I will transpose it because I want the decision variables to be so it is a bit more visible. I'll attach it. And these are called my decision variable. Okay, I'll keep that. Now here below that, I'll have the cost coefficients. Now cost coefficients are here. I take all these cost coefficients, Control C, you transpose it, be special, transpose. Okay, these are my cost coefficients. These are my decision variables. These are my cost coefficients. These are my cost coefficients. And oh yeah, these are my decision. Great. Okay. Now I will have the constraints. I have my constraints. Now constraints, I'll keep that separately. First constraint is dry land. Farmer will have dry land. He will have irrigated land. He will have labor requirement, all your resources, labor requirement, working capital. And you could add more, but I'm just showing you a small example. Then he has a demand. He has a demand. He has a demand for rice, for paddy, for paddy. He wants 1 quintal of paddy, and he has a requirement for milk, which is demand, right? And yeah, so this is how you set it up from the data. Now I take the constraint. Now this is a very important constraint that I should know how to tell this. Minimize it. So you can see. Okay. Now here what I do is now this is this. These are my costs. These are your C's. What I call C in the problem, no? Which we call C. I'll put it light pink. These are my C's. Right. These are my B's. I'm going to put my input output coefficients, which are these are my C's, cost coefficients. Here I'm going to put my input output coefficients. Here we have 2. Here we have 3. And put a different shade, light blue here, and it continues here. Demand. The demand will be done, right? And these two. Okay, these are my B's. This is my C, just for you to understand what it is like, looking like. Okay, these are my B's. So here, what I say is, how much dry land? Let me just put a figure here. I've got 1.80 acres of dry land, and I've got 1 acre of irrigated land. So these are my resources. The constraint is also related to resources. I have about 200 man days available with me. I'm going to supply my family labor, 200 man days. Working capital, I had got with me, I've got about a lakh. I've got a rupee with a lakh. Now, paddy, what is my requirement? I want at least 1 quintal. Milk, I want at least 120 liters per season. So these are my B coefficients. If you want to see what it looks like, These are very coefficients. Now we have defined the C, we have defined, you know what is X, and now let us see what is A. A. Now A are the input output coefficients, which I get over here. Are the input output coefficients. These are my input output coefficients. Now the input output coefficients of land are put like this. Now paddy does not grow on dry land, so I just put nothing here. Maize grows on dry land, cotton grows on dry land, jawar grows on dry land, groundnut grows on dry land, soybean grows on dry land, and red grain grows on dry land. Now irrigated land, paddy, irrigated maize, irrigated cotton. Yeah. So I think that gives you my, because the dairy does not require any. So now coming to these constraints. Greater than, equal to, less than. I'm now going to put that. So dry land always has to be less than or equal to. Okay. Less than or equal to. I can't grow more than 1.2 acres. You see, it's also irrigated land. Labor, of course, I'm limited to 200 man days. Working capital limit, it's all less than. But when it comes to demand, for instance, I want paddy, I should have at least, so greater than or equal to 1. Don't put less than or equal to 1 because it will not satisfy. And for milk, it's also greater than or equal to 1. So demand. So I've just put these kind of demands that I want. Now I want to also put another constraint which is called intercrop. I want to do intercrop. So whenever I grow cotton, for every, this is hypothetical, it's a little hypothetical, for every 4 lines of cotton, I want 1 line of red gram to enrich the soil. Okay, I want to do this balance. So what is it? For every 4 lines of cotton, 1 line of red gram. So the utilization of land is in the ratio of 4:1. 4 of cotton, 1 of red gram. But when we write it over here, we'll write 1 under cotton and 4 under red gram, 4 under red gram with a minus. And this constraint should be made equal to 0. Only then it will balance. This is very important. Please understand this. Okay, this is very important. So in terms of to bring this down. So this is also an input output. So I'm just showing you a small input output coefficient in order to make you understand, right? So now we've set up the problem. Now we have to set it up for solving. So this is how a linear programming problem is set up. You can see this where this is how a linear programming problem is set up. Now I want to prepare it for solver. So when I prepare it for solver, there are certain some little things that I should take care of. Now what happens is, if I specify in my linear programming, the objective function is 1250 into paddy, 5680 into maize. If I do that, then the problem is it will get overwritten. So whenever the result is written, you won't know what is. I'll get a value like 1.1 here. You won't know what it is. So to overcome that problem, what I do is I create a blank cell where I want the result to be written. So this I will make it 1 yellow. Okay, this I call changing cells. This I call changing cells. So we'll continue. Now we'll have to fill up the coefficients for labor, working capital, fodder, farmyard manure. Demand, we've already said. Demand, if the requirement is 1 quintal, then you should put the yield per acre as the coefficient. The requirement is only 1 quintal, but the yield per acre should be the coefficient. Similarly, for milk, if I want for 1 liter per day for 120 days, I should get the total production for the season per cow. So that should be the coefficient. Now we need the coefficients for labor, working capital, and so on and so forth. So we go there. and we'll get the labor coefficients. You just have to prepare this and copy it and paste it over here. Expression and transpose. That will be the labor coefficients. Similarly, I will get the working capital coefficients. And then fodder, how much of fodder is produced. So I have to get the fodder produced. I'll just take this one. Fodder, and finally the FI. With the coloring. Okay. Now what it does is it takes the farming labor and restricts it to 200 man days. It takes the working capital, restricts it to 2000. Particularly when it comes to fodder. Now fodder is the output, and this is used by the cow. So the requirement per cow is 12 tons. So it takes 12. So just like we say, it's 2.5, and this is 20. This is 25, and this is 20. 20 quintals. Okay, and the requirement is 120. The requirement is 120 quintals. So when this is the output and this is the input, the sign should be reversed. One of them should have the opposite sign. One of them should have the opposite sign. So what we do, we put a minus 120. Minus 120. And if you think the positives are going to be greater than the negative, then you make it less than or equal. Otherwise, if you make it equal to, it will restrict, it will restrict. And less than or equal to 0. This is important. Similarly here, this is consuming and this is producing. So we can put a minus for each of these. We can put a minus for each of these. And the positive, this should be, if you think the requirement will be greater than this thing, then make this greater than or equal. This has to be done carefully. It can be altered. This more or less it has been set up. More or less it's been set up. Now we are going to set it up in solve. So we go to data, click on solver. And then it's asking for the objective function. So you click on this, select the objective function, put it down. And then it's a maximization, minimization. It's a maximization problem. Which are the changing cells? The changing cells I have deliberately marked it separate from the variables so that it does not overwrite the variable names. Then I'll add each constraint one at a time, less than or equal to this. Add this constraint less than or equal to this. Add this constraint less than or equal to this. Add this constraint less than or equal to this. Add this constraint less than or equal to 0. Add this constraint greater than or equal to, greater than or equal to, I should put a 0 here, it's not there, 0. Then add this constraint should be greater than or equal to this. Add this constraint should be greater than or equal to this. Add the last constraint should be equal with this equal to this. And I say, okay. So it's all been set up. Then I just go here and select simplex solve. And it says, solver found a solution. All constraints and optimality conditions are satisfied. Then we say, okay. So what it suggests, is that you should grow soybean on 1.67 acres. You should grow a little bit of paddy, and you should have 2.3 dairy cows. This is what I told you about the divisibility part. It assumes that it will take round numbers, right? Now you can just about see less than or equal to uh, 5,900. That's that. Okay, right. Well, so it's requirement of fodder greater, and then it requires what we call the fodder is in surplus. So now once the solution is being done, right, you can examine this like this. Okay. Now you've got 1.76 acres of dry land. It is utilized all the 1.6. You've got 1 acre of irrigated land, but it's utilized only 0.3, 0.03. This is a problem. This labor has been fully utilized. Capital has not been fully utilized. It's used up only 59,000. Uh, this is okay. This is less than 0. This will be greater than, okay, all is fine. This is equal to 1. So it's produced that much. It has given you the amount of milk that you require, much more than what you require. And also your intercrop condition has not been affected because we did not put it to prescribe a little bit of cotton. So red gram was also very small quantity. So this is virtually 0. So no problem. Not a bad issue at all. Now, the problem here is now I know I'm not happy that look, irrigated land is not fully utilized. So, sorry, irrigated land. So, the kind constraint that I observe is labor. So, what I should do is I should provision for hiring labor. So, for that, what I do is I'll insert one column. Okay, I will insert a column. And here I'll call it hire labor. I will put the wage rate. I will put the wage rate with a negative sign. So let's, for the time being, I just put 100 rupees just for the sake of illustration. And in the labor column, because resources are going to come into the system, so I put a -1. So when resources are coming into the system, I put a -1. When resources are going out of the system, I will put a +1. So I just put this and then just see anything has been affected. Now, since I put it in the middle, all these coefficients, these formulas still hold. Okay, so okay, now I'll go to solver and I will solve. It's give me a solution. And 579 units of labor, 597 man days of labor has been hired at 100 rupees. I think this 100 rupees is too little. So I'll make it 252. Okay, just for illustration. And that's okay. And 563, the full labor is still being utilized, even at 250 rupees. Let me make it 400 rupees. And solver and solve. And there's it. Okay, no, 400 is too much. Then I'll do -350. And then I go to solver and solve. The 350,000 winner to say 300. I'll put it back into it. Okay. Now, capital is fully utilized, labor is fully utilized. I'm hiring 560 man days of labor. My soybean has gone up to this thing, and dairy has become 11 cows because that's the most profitable. That's the most profitable, using very little of this thing of working capital. It's got very little working capital requirements. So they're prescribing. So now I want to restrict this dairy to not more than 3 cows. So I put one more constraint. I'll put a cap on dairy. The constraints. So I say dairy should not be more than 3 cows. I say 1 should be less than or equal to 3. The constraint equation has to be extended, and you will just see by going formulas, and I say show formula. It shows me how this thing is working. Numbers. Take it out, and I say trace precedence. It shows me exactly what it has. It's multiplying that row with the changing cells row. So it's okay. So I'll remove the arrows. And now I will go to solve it. Okay, and now go and solve it. I'll go to data, solver. Oh, sorry. And then I have to add one more constraint. Now this is a constraint. If I don't add this constraint, so I say less than or equal to 3. 3. So this is, say, okay. And so now I can put the constraint works. Solver. Then there's row 16. 16. Change. This one. Less than or equal to this one. Less than or equal to this one. So that is done. And I say okay. Let's change the body. And I say okay. Now I have restricted to 3. Labor is higher has come down to 39 because I think dairy requires a lot of labor. It does not. This thing it comes down to 39. Grows a little bit of ragi, mostly soya bean, and the irrigated land is still not utilized. Irrigated land is still not utilized. I want to do a diagnosis of that. So I go to solver. I say, okay, before I say, okay, select answer, select sensitivity, select limits, and say, okay. Now I want to know why cotton, maize, and all are not getting included. It will give me two of the things. So first I'll go to sensitivity. So I will now go and look at the crops that have been grown. The crops that have not been grown are maize, irrigated maize. Now the problem is now with irrigated maize. Now what he says is, look, if irrigated maize is now presently giving you a profit of 7,000. Unless that profit can be increased to 17,500, it is not going to get selected. So I have to add this allowable increase. So what it tells you is, this is the present coefficient. If you want the solution to change, you should increase this coefficient by these quantities. So which means I should increase my maize profit from 7,000 to plus this, that is 17,500. So let's leave out maize. Let me take cotton. Cotton is now I'm getting a profit of 23,000. I should get a profit of 23,800. That is 23,000, 32,000. That is 31,000 plus 120, 32,000. And let me look at paddy. Paddy, I'm getting 12,000. I should get 24,000. So the yields have to double. So assuming I'm going to grow a better variety of cotton, say for instance, I'm going to grow a better variety of cotton. Now the profit is going to come to 23 plus 8, 31. I'll make it a little more, 31,500. I'll come here and make the related cotton 31,500. And then I'll solve. Now, 1 acre of cotton has been grown. All my irrigated land has been utilized. All my dry land has been utilized, and I'll make a profit of 60,319 will be my net profit. I'll have 3 dairy cows. I'll have 1.76 acres under soybean. I will hire 159.68 people, and I'll put roughly 0.696 acres under paddy and cotton irrigated, and I'll have a little bit of I'll have a little bit of paddy just to meet my house requirement. Now you may wonder what happened to the intercrop. Now the intercrop that I set was only for irrigated cotton. Sorry, dryland cotton. And now let me set it for irrigated cotton. So the moment irrigated cotton is grown, then also red gram will also have to be. So I just show you how that works. So solve cotton disappeared. So cotton disappeared because it is not profitable to combine it because the profit will come down to 59,000. So that thing is not being done. So I'll retain. I'll take out this and retain it there. So which means the intercrop reduces the profitability of cotton. Because the intercrop is not profitable. Intercrop is not profitable at this level. We'll go back to the sensitivity report and take the red gram. Now, red gram has to increase by 71,500 for it to include. It's just not feasible in your cropping pattern. And that is why the moment you put the intercrop for cotton, it says, no, don't grow cotton also because it will greatly reduce the profit. And this is how a linear programming problem is solved.